Can you hear me? Hope everybody got the beverage of their choice. So let's try to do this. If I'm not loud enough, tell me. If I'm too loud, tell me as well. If I'm too fast, which I tend to be, then tell me especially. First, Adam and I are very privileged to be with you tonight, and that you're giving us your time. And thanks to the organizers for inviting us. So let's do this. My name is Robert Nikutta. I work at NOAO. In my day job, I'm a data service scientist, and in my spare time, I'm an astronomer who works on active galaxies. So the first thing to get out of the way, what I want to talk about is these kind of things. And I have a laser pointer, but I think I won't have to use it often. These kind of things. So things that look like a donut, or if you prefer the Majesty's language, donuts with O-U-H-G-H. So basically, a thing that is matter in a ring structure, but has a hole inside. And it's a stark contrast to something that I know from home. I was born in Poland, in Eastern Europe, and donuts look like this there. They were very delicious, I remember. So when I was 12, we moved to Germany. My family moved to Germany, and donuts looked like that. They had something in the center, but it's not a hole. It's filled usually with some jam or something. By the way, this is called a Berliner in Germany. So when JFK was in Berlin and gave his speech, he gave people a laugh. Although not in Berlin, he was safe there because, except in Berlin we call it Berliner, but in Berlin we call it something else. Then a few years ago I lived for a couple of years, actually more than a couple of years, 4 years in Chile, South and South America, and donuts look like that. They also call Berliners. All of the Spanish call them Berlines. And there are some, gigantic abominations of calories filled with a thing that is called manjar, the brown thing in the middle. It's like a cream made from caramelized milk and sugar. It's amazing. So, anybody from Texas here? No? So, look, you recognize the flag? Top right corner. This is Texas on the bottom, and this is Chile. I don't know why they're so similar. I tried to Wikipedia, but to no avail. It's the same flag. So back to science. So donuts in space. That's my topic that's the subject of my talk. I want to talk about these things that are those. And now I need a pointer. I think these things. Is it actually shown? I think so. Yeah, these things, not the center. So the center is a supermassive black hole. I've been to several spacecrafts. Have you been before? So you've seen some talks maybe where supermassive black holes have been explained. Every galaxy in the universe, we think, has a supermassive black hole at the center. That's a black hole that has the mass of millions to billions of the masses of our sun. It's amazing. Some of them are active galaxies. And that's always, I will explain later, is when something's happening in the center where lots of light, lots of energy is produced, very violent processes. But what I'm interested, or what I want to talk about to you today, is the thing surrounding that whole thing. And it's colder material, it's not as hot, and it's in the form of dust. It's not the kind of dust that you know from home, from your kitchen or from your living room. It's kind of more like a soot, something that will come out of your car, on the back of your car. It's molecular material, it's coldish, it's like 100 to 200 Kelvin maybe. In the center it's much hotter. And it's a lot of it, so it's very opaque. When you look at it from our point of view, edge on, you will not see the center black hole and stuff that's happening in there. But in infrared, I will show you can actually see through, because infrared light can penetrate this dust. By the way, this is an artist impression, it's not a real picture. And we'll see lots of artist impression tonight. So, some words of wisdom. For any problem in astronomy, there exists in the order from pretty to ugly. Artist impression, the most pretty. Model cartoons, so but easy to understand. Actual models, kind of ugly, kind of simple. And then data, just the crappiest thing of all. Because usually we're pushing the limits of what we can observe with the current latest instrument. So, I have to say though, whenever we build a new instrument, we produce beautiful, gorgeous data. And everybody's enchanted by it until the next instrument comes along and we forget about the old stuff. So back to this slide. This is an artist's impression here. And what I want to talk about is the torus, the ring surrounding the whole thing, which is dusty. And I want to argue later it's clumpy. So it's not homogeneous like here, but actually made up of discrete clouds. And it's around an active galactic nucleus. I'm going to explain that too. So, quiz. Not a quiz question, but a quiz. What is it? Artist's impression, model, or data? Right, artist impression. Very beautiful torus in the center. We're looking edge on. We cannot see what's happening in the center. It's in the galaxy. You see the stars in the background, and there's some powerful jets even coming out of it. Wonderful. Another one, I like that one. Looking kind of into the thing. Something's happening there. It's a huge concentration of mass. Yeah, you can see there's dust around it, and as you get closer and closer to the inner center, it gets hotter and hotter, and in the center, matter is falling into the black hole. It gets so hot while it's rubbing, viscously on itself, that some of the light that is coming out of it pushes material out, and you see a wind of material being launched from the center. Here another one, the whole galaxy seems to be spiraling around it. The torus and the accretion disk and the black hole are in the center. You cannot see them, but in the winds launched from it, you see like little dots, stars, stellar nurseries. There's actually stars being produced. We think actually that's what could be happening, but it probably doesn't look like that. This is again an artist's impression. And here from this year, my favorite, a zoom in of the action in the center. There's a black hole, little black dot here. The black hole itself is probably much, much smaller. It's just an infinitesimally small point at the very center. But around it is a radius of orbits that where the orbit speed will be higher than the speed of light. So nothing can escape because nothing can be faster than the speed of light. So when even light enters or material enters, it's stuck to forever. So this radius, called Schwarzschild radius, is black. There is nothing, penetrating it or coming out of it. Around it, you have this hot gas. This is the accretion disk, where temperatures of hundreds of thousands of Kelvin or even millions of Kelvin can be reached. And further out, you have this wispy, dirty-looking material. This is probably the torus or the outer parts of the disk. In this artist's impression, again, it's one. You see that on the right side, the material looks red. And on the left side, it looks bluish. And that's simply because the artist wants us to convey that the disk is rotating. And as you probably know, if it's rotating, this part of the disk rotating on the right is rotating away from you, so the wavelength will stretch a little bit and become redder. And on the other side, it comes back to you, so it looks bluer. So, beautiful artist impression, amazing detail. I mean, it's amazing. But have you seen the best actual image of an Aegean torus yet? Be ready. Are you ready? This is it. That was just produced this year, with data taken last year, but it was produced this year. It's pretty convincing that this is a torus of one particular active galaxy, one of that's very closest to us. That's kind of, by the way, I want to point out, the color coding here is artificial, that's not really how it looks, but the blue color was assigned to the part that's actually rotating towards us, and the red away from us. If you notice, it's the opposite direction from what the artist envisioned. So artists can be wrong, but scientists sometimes do. So where is this thing in the universe? So we are in our galaxy, and we're looking outside, and we can see many, many other galaxies. This is one of them. It's pretty close for an active galaxy. It's called NGC 1068. Has many other names as well, but it's the most famous. And it's a galaxy that is, if I remember correctly, 14 million parsecs away. That's something like 42 million light years away. So the image that you see, taken today, is 42 million years old. Dinosaurs were dead already, but mammals were just starting on Earth when this picture was produced, and then traveling to Earth. So at the very center there's a bright thing. At the very center there's probably something about the active galactic nucleus. And here is a zoom of it. On the left you see the same galaxy, different picture though. And in the zoom window you see recent observations with ALMA. I will show you ALMA in a second. And you see, hopefully you see, you see a green ring of material. And that's not the torus. That's cold molecular material that can and is producing stars in a ring surrounding the whole thing. The diameter of this is hundreds of light years, hundreds. But what we are talking about is this tiny blob in the center. Just this. This is the torus. And it's only 6 parsecs across in this particular source. It's tiny in comparison. Still huge, but tiny in comparison to the galaxy where it's in. And then one more zoom. This is the picture you've seen. So this is actually the data, this time color-coded based on the radial velocity coming towards us, away from us. Amazing. It took really 30, 40 years of theory and 25 years of conceiving instruments and building ALMA and getting to that point where you can actually produce the data set. And I would say €1 billion to build it. So ALMA, nobody's seen it already, but in 2014 I was lucky enough to go with a friend up to the mountains and see ALMA. So the picture on the left is actually one panorama, but I cut it in 4 pieces because it wouldn't fit on my screen. And so from top to bottom, basically left to right, you can scan. It's a huge plateau at 5,000 meters elevation. I took my phone out with the GPS in there, and you see there's 5,071 meters above sea level. That's the altitude where it is. AMA is an array of close to 70, like 67 or so antennas, each of them very identical, 12 meters in diameter, very high precision, with fantastic radio receivers. Actually, radio is a misnomer. They use millimeter and sub-millimeter radiation, wavelength of radiation, and that's where the name AMA comes from, Atacama Large Millimeter Sub-Millimeter Array. The point of having 67 antennas is that you can spread them over a large area, and then when you combine the signal afterwards, you get the resolution of a much bigger instrument without having to build a much bigger instrument. It's too expensive and impossible. So here on the left you see one of these antennas being serviced by technicians or engineers. They're probably changing or servicing the receiver, which are housed here. And you can see in the picture that they're all wearing oxygen tanks. So not the kind that's used for scuba diving, much smaller and not pressurized mask or something, but just like a nose thing, and that gives you a whiff of oxygen each time you want to breathe. And I need to breathe on toes. Because at 5,000 meters, you cannot really work for a long time or do any kind of exercise without oxygen supply. So here on the right side, you see my finger clipped to an instrument, to a little device that measures my heartbeat. This is a few minutes after arriving on the high side. So the control center, the headquarters, everything is at 2,000 meters, there's a base camp. But then you can take a pickup truck with an experienced astronomer who works there, and in an hour or so, you're at 5,000 meters. And then you monitor, you measure your heartbeat and your oxygen saturation level in your blood. So the 112 on the left, on the right, sorry, this is my heartbeat after arriving, and 90% is the oxygen saturation. A healthy normal oxygen saturation is 95 to 100% at any time. And then 10 minutes later, 81. So dangerously close to where you should probably go down a little bit. And so we stayed only half an hour, that's typical without oxygen. And the interesting thing was, the guy was explaining to us everything, and after 10 minutes he asked us, so how do you feel? And my friend and I looked at each other and said, I can't follow you, you're too fast. He said, that's correct. If you told me you feel super, you feel euphoric, you feel fantastic, we would go immediately down emergency because you are experiencing altitude sickness. So if you feel that without oxygen, that's good. So by the way, AMA is at 5,000 meters. It's a whole plateau surrounded by some mountains. Some of them are ancient volcanoes, some of them are still active. On this ancient volcano, there is a telescope up there, built by the Japanese, a small telescope. They're building a bigger one now. The telescope and the observation room is up there at 5,640 meters, and people stay there overnight and observe. And the room that they have is not pressurized to simulate some low altitude. So they're actually wearing oxygen masks when they're observing all night. So crazy people, but the claim to fame is that they're working at the highest permanent observatory in the world. Permanent because you can send instruments in a balloon or something, but it's really not. Okay, back to science. So like I said, we're talking about a ring of material that's dusty, clumpy, around active galactic nucleus. What is an active galactic nucleus? I explained a little bit. But one of the first characteristics that every galactic nucleus is that there's an extremely bright point source at the center nucleus of a galaxy. So what's the point source? It's the source of light, I guess, choo-choo. Can you still hear me? Okay. So a point source is an astronomical source of light that is so small that even with the largest telescope, you cannot resolve it. So if you look at it, all the light from that source is concentrated in one pixel of your camera. And if you make the pixel smaller, you still have only one pixel that has the light. So it's too small to be resolved. It's really tiny in comparison to the galaxy. A word of warning though, sometimes the point source that is claimed here to be one characteristic of AGN, of active galactic nuclei, is not visible. If you look at the optical light, like here with an instrument taken with a VLT instrument of a famous active galaxy nearby, Centaurus A, all you see is the galaxy and some dust. The dust lanes, by the way, this is on galactic scale. This is not the Taurus. This is much, much further out and much more of dust. This is probably another galaxy that has been swallowed by this big one, something like 70 million years ago. And the material being no use to produce new stars and things like that. All the glow, not the stars. The stars are in our own galaxy. This is just like looking through a tree through a forest to find a specific tree. You just see all the trees, right? So in our own galaxy, if you look out in the big distance, you have lots of stars in the foreground with our own stars. But all the glow, this is the combined light of all the stars from the other galaxy, from Centaurus. It appears as a glow, all smeared out, because we cannot resolve the particular stars, the specific stars there. So where's this central point source of light? In optical, it's hidden by the dust that you see in the middle. But if you look in infrared, the same galaxy, the same picture, all the glow disappears, all our stars disappear because they're not very bright in infrared, and infrared penetrates dust. So what you see is the point source of light, very bright, so bright that it outshines the whole galaxy. It's brighter than the rest of the stars in the whole galaxy. And there are probably 200 to 300 billion stars in that galaxy. All that light together is less than what comes from the center. And imagine the center is just a few light days that are in size. It's amazing. So another characteristic of AGN is the nucleus, the very center, has a non-stellar spectrum. What? What do you mean? I don't understand what you're saying. Non-stellar spectrum? What's a spectrum? I'm checking who is 35 or older and gets the reference. So let's see if Pinkford got it right. This is a real experiment of a prism with a triangular piece of glass that is that tall, and you shine white light from the left bottom. And you see, they got part of it right. Some of the light gets into the prism, but some gets reflected as well. And then when it travels through the prism and exits the second time, it spreads into a spectrum. So the different colors of the white light, they bend at different angles. And so when they exit the prism, they make a rainbow. And so the rainbow is a spectrum. If you measure the intensity of the red part of the rainbow, and the green, and the yellow, and the blue, you would have a function that is a spectrum, which is how much intensity as a function of color or wavelengths you have. So that's a spectrum. What's a stellar spectrum then? It's a spectrum that a star would make. Stellar star. Our sun is a typical star here on the left. And here on the right, you see a function that describes the spectrum of a star like our sun. It took a while to figure out what the function should be. And in 1900, Max Planck derived the correct formula. It's called a black body spectrum. The function is complicated, but very simple. It has only one key parameter, the temperature. You plug in a temperature, you get the curve. You plug in a different temperature, you get a different curve. So you see, for instance, there are several curves for different temperatures of the black body. 3000 Kelvin, 4000, and so on. As it turns out, our sun, the surface of the sun that produces all the light we're seeing, is about 6000 Kelvin in temperature. So the highest curve here is roughly what the sun is producing, and to a great degree of accuracy. And so the spectrum is how much light, intensity, as a function of wavelengths it produces. And not only in the visible spectrum, where you see the rainbow from blue to red, but also beyond red, which is infrared. And here on this side, beyond blue, which is ultraviolet, and then X-rays, and so on. So that's a stellar spectrum. But I said the nucleus has a non-stellar spectrum. What does it mean? So if you take a galaxy and it has 200 billion stars in there, and all the stars have different temperatures, but each of them produces a black body, very similar looking function. What do you get if you add that light? Exactly, yeah, you're right. You get like a broadened emission of a black body collection. 300 billion of them. Some are faint, some are bright, some are blue, some are red, but all of them make a curve. And in this graph, and I promise this is the most complicated graph in my whole talk. This is again, wavelengths, and this is energy, how much light. And this solid line here is the spectrum of a galaxy. All the combined light from all the stars in a galaxy. Typical. Some look different or something, but this is very typical. You see it's one big bump, broadened, that's it. But if you look at all the black dots, there are data points from, I don't know why there's a feedback. There are data points from an active galaxy. And you see it looks very different if you connect those dots in your mind. For instance, there is a very broad peak here in the infrared. That's the dust in the torus that's producing this. The dust gets hot, and something that is hot, a black body, emits in the infrared. It's heat radiation. And here in this blue part, it has a very blue bump. We also call it a big blue bump. And that's optical light, that's UV light. And if you look into the galaxy and there is an accretion disk happening, that might be, for instance, the light from the accretion disk where really hot materials being churned and destroyed and swallowed into the black hole. Then some active galaxies are also very bright in X-rays and gamma, some in radio, this one not, but some are. So it's a whole spectrum that looks very different from a stellar spectrum or even the combined stellar spectra of one galaxy. Okay. So the last last definition that we need for active galactic nucleus, that some activity is happening, right? It's active. And I explained already before, activity means matter, some star got in the way and got disrupted, or some cloud of gas and material flies in and gets caught by the gravity, by the gravitational pull of the black hole. And it starts orbiting. Is it because it's like a feedback all the time?
Yeah, I think.
Okay, try this way. And so as it's being swallowed and orbiting into the black hole, slowly it heats up, and at the center produces huge temperatures and lots of emission of light. That's called activity. Now imagine a star gets disrupted, swallowed, all the material is processed, falls into it. What happens when it's done? It stops heating, it stops being active, and it becomes a normal galaxy. It's a bad name, but we call them normal, non-active galaxies. So how do we know there are black holes? We cannot see them, right? They're black. But like I said, we cannot know, because they're swallowing a lot of material, if there's hot material around them at the very center, that there must be a black hole doing this. Although we don't see the black holes. There are other ways of figuring out that, or deriving, deducing that there are probably black holes somewhere, supermassive black holes. But the best thing of evidence, I think, is in our own galaxy. Our own galaxy is non-active, but it has a supermassive black hole as well at the center. And if you look with infrared telescopes to penetrate all the dust that is between us and the center of the galaxy, our galaxy, if you look with infrared telescopes, you see stars orbiting at a point. The point is invisible. It's marked here with a yellow cross. That point is the derived location of the black hole, called Sagittarius A star. It's in the Sagittarius constellation, and A star is the location. So this is going to be a short video of several years of observations, and all the points here are stars, actual stars, moving on orbits around that black hole. Let's see. The time is on the top left. And in a second you will see a zoom in where you will see one particular star. Yeah. Pay attention to this guy. Can you see it? This one. It's called S2. That's the name of a star. How it comes and makes a full orbit. We could observe a full orbit of it. And did you see how when it gets close to the black hole, it just swings around it. It's on a highly elliptic orbit. It's still a capital orbit, but highly elliptical. And we can follow it for longer. Exactly. When they come closer to the center, they gain speed. And when they leave, they are feeling the pull back again, so they slow down. Like planets in our solar system. So, from the motions of these stars in our own galaxy around this point, we can deduce that there is a mass concentration at the center of, here comes the trivia question, how massive is it? What's the mass of the supermassive black hole in our center of our own Milky Way? Is it A, 200 times the mass of our sun? Or B, 3,000 times? Or C, 4 million times? Or D, 5 billion times the mass of our sun?
C. Right here. Raise your hand. C. C. C.
And the safety thing, so I don't give it away too early. Yes, it's C. What did he win?
A poster and a sticker.
Oh. So cheers to the winner. So indeed, 4 million times the mass of our sun. You have to imagine, to produce such a black hole, you have to swallow 4 million suns. It's amazing. And yet, among the galaxies, this is lightweight. There are many, many, many galaxies there with supermassive black holes that are 1,000 times more massive, billions of solar masses in their centers. I can't comprehend it after doing astronomy for so many years. So, the picture of the objects we're talking about emerges like this. And this is a famous cartoon of a model. It's not a model, but it's pretty, and it's been overused in papers so many times. So, at the center you have a black hole, this black dot. Around it, you have an accretion disk of material that gets swallowed. It has to spiral in, it cannot go straight because of angular momentum conservation. But it spirals, angular momentum is carried away, but the matter is falling in. And some of the matter is converted into pure energy very efficiently, much more efficiently than nuclear fusion. Nuclear fission, we think, is like 10%. Nuclear fusion is, I think, 2 or 3%, and nuclear fission is like 4.5%. So this is one of the most, if not the most, efficient energy conversion mechanism we know. And then some energy is flowing out as light, as matter. There are some jets in there, we'll talk about it in a second. And there's this molecular dusty thing around it we call torus. There's lots of debate whether it's a torus or it's a wind or it's a bagel or it's a disk. Doesn't matter, it's all names. These jets, you've seen this several times already, artist impression and in this model here, in this cartoon, sorry. They really exist. This is two pictures of the same galaxy, M87, very famous, very big, one of the biggest elliptical galaxies. All the glow here again is stars. We cannot resolve them, but there's billions of them, hundreds of billions of them. And then at the very center is the active galactic nucleus. And one clear giveaway sign of that is always when you see a jet like this, coming out from very center and extending 2 kiloparsecs. That's like 6,000 light years. Isn't that amazing? And it's not light, it's matter, it's particles, it's electrons and heavy particles being accelerated at the center, close to the black hole, by magnetic fields presumably, and collimated to a fantastic degree. The collimation, how narrow this beam stays, is better than my laser pointer, which is supposed to be the perfect beam, but it's not. So this is material flowing at fantastic velocities also. This is fractions, significant fractions, like maybe half of the speed of light. Matter traveling with the speed of light, or half the speed of light. It's quite mind-boggling. Here another one. You've seen this before, Centaurus A, but without the jets. Here is a picture where you see Centaurus A, the galaxy with the dust lanes in between from another galaxy that it swallowed. But overlaid in blue and yellow are data from radio observations. Jets that are at some oblique angle, doesn't have to always be perpendicular. And then where it hits the outer materials that are, the outer ranges of the galaxy, it kind of shocks material out there and excites us to be luminous in radio light. So, what I do is modeling. Is this a model, cartoon? Artist impression? That's actually a model, thank you. That's actually a model, yeah. So what I'm interested in modeling is how when the light from the central source hits the torus and it starts to heat up the torus, some of the dust is evaporated at the front, but then the light penetrates into it and makes it hot. And then the heat has to be released again somehow, so it's released in infrared light. And what you see is a model. For now, first we're looking top down, we're looking really into it. So at the center, there's not a black hole, this is just the radius where dust cannot exist. It will be evaporated, it's too hot. Dust can only survive temperatures maybe at 1500 Kelvin. The specific dust like graphite can go higher, 1800 Kelvin, but not much more than that. So everything up to this boundary is evaporated, can only exist as gas, but not as dust. But here, at the boundary, it becomes cool enough for dust to form and to persist. And so the photons, the light, penetrate this structure and make it hotter, and the heat comes out as infrared radiation. And you see a composite here of 3 different wavelengths, 2 micron in blue, that's the very center, the hottest, in green, the 10 micron, which mostly is interesting for if you study dust, and then at here 22 micron in red. So the movie is going to go that we're looking at the same source, but we're moving from top view to the edge view, back to the bottom view. So let's see how the light looks. So the arrow there on the bottom shows you the orientation. So we're going to see I stop at 45 degrees now. You're looking, if this is the torus, you're looking at that angle. So what you're seeing is the hot piece of gas here, piece of dust here, and some illumination. But the stuff in the front here, you don't see, it's black because there's the dark side of the dust. You're seeing it's not illuminated. It blocks your line of sight basically. And if you continue to edge on, here look very symmetric now, but you see, at least on my left, I see, it's hard to see here. All this white stuff is mostly from the blue, and all this stuff out here, it's kind of red from here. So this is the cold dust in front of you and away from the source that makes this kind of pattern. And then the last point I want to make, I mentioned that we think that the torus, dust in the torus, is cloudy. It's cloudy. It's not one homogeneous mass like here in this model. So we model this too. Again, question: is this a model? Cartoon or artist impression? I take bets. It's not a model. It's a cartoon, but with as a movie. But in principle, the model works the same way. So at the center is a source of light that is not depicted here, but imagine it in the center sitting there and irradiating everything isotropically with the same kind of light. And then the camera flies around it, and there's a collection of dust clouds. You see, it's not a homogeneous mass, it's just dust clouds distributed somehow. And why it's important, I fast forward a bit till we see edge on. Why it's important that if you have a clumpy distribution of dust, and if you're looking edge on, you still see some of this bright hot stuff from the far side. If it was homogeneous, you would not see that. but in observations we do see it. And so we think that it has to be clumpy, otherwise we could not see this kind of pattern. Yeah. And now, where's the projector? That's too high.
Yeah.
So I wanted to make a shadow. So imagine there's a source of light, and my hand is the cloud. If I move in, of course I block the light there. And so can we see that? If the clouds are really moving there, could we see that looking at the source and observe for a while and see whether actually something's happening? And in fact, that is what's happening. So this is the flux, the light, measured in some specific band of X-rays over time. And you see, it's very noisy because X-ray data is very sparse. But for a particular source called Markarian 79, which is an active galactic nucleus, there's some gap in data, but then there's some, some data moving on. This is time, moving from left to right, and moving. And at some point, there's a dip. The amount of light suddenly shuts down to a much lower level, stays low for a while, and comes up again to the old level. The best explanation for this is a cloud of gas moved across the line of sight, blocked your view, and then moved away again. So we're modeling this as well, and this is an artist impression of, but based on a model that we did. So we had a paper in 2014 with colleagues, and then we had a press release with NASA showing a picture of the day, where we had two versions of the video, the same video. One was, not this one, where in the top right, we had like little weather symbols. So if a cloud was in line of sight, we had a cloudy symbol. And if it was out of the line of sight, we had a sunny symbol. So like space weather, basically. But I think after this talk, I hope you are experts, so I can show you the scientific version of this video. So it's a sophisticated artist impression of a model that we made, where clouds of dust are orbiting a supermassive black hole, accretion disk in the middle, some jets even, just for show. And then on the top right, you see a X-ray spectrum. It has the shape of spectrum. This is X-ray energy, so basically wavelength, and this is how much X-ray light is coming. And whenever the camera is moving and the light of a cloud passes the line of sight, it will dim the spectrum, and you will see that very clearly. So, go on a bit. So we're looking like from bottom into the center, and now the clouds are moving, and observe the spectrum. Whenever a cloud is moving by, the spectrum is dipping. And now we really start moving into the equatorial plane where there's more clouds. When we get into the equatorial plane, like really edge-on view, look at the spectrum, it goes away completely. All the X-rays are absorbed. And this happens really. We observe even some AGN where they appear super bright, we call them type 1. Everything is smoothly and peachy, and then suddenly it goes away. And a week later, a month later, it comes back. So we think this is what's happening. The clouds are moving in local line of sight. So I'm at my last slide. I learned somewhere that every talk should have 3 takeaways. So here are mine. I hope you can take them home with you. Active galaxies are those galaxies that eat matter at a given time. If they don't eat matter, we just call them normal, boring, non-active galaxies. The eating machine at the very center is hot and violent. There's lots of stuff going on. There's so much physics. We don't understand half of it, I would say. We have clues. We have some simulations, theoretical, and better observations. But you've seen the observations we have so far, leave much to be desired. And then my last point is that the active black holes then are often surrounded by a thick donut of dust, which I argue is lumpy. Thank you very much.